Imagine holding a guitar string and strumming it. The different vibrations it can make are analogous to the core concept of string theory. Just as a guitar string can produce different notes, the fundamental entities of our universe, according to string theory, are tiny vibrating strings of energy. These strings oscillate, and the various modes of vibration give rise to the different fundamental particles that we observe. Now, this might seem unusual, especially if you're familiar with traditional physics. In the conventional view, particles are considered as points with no size. They're as small as you can get. But string theory challenges this idea. It says, no, particles are not points, they're something else, they're tiny strings. And these strings are ridiculously small. We're talking about a scale of size that's so minute it's almost impossible to imagine. It is at this minuscule level that these strings vibrate, each at their own unique frequency. And it's these different frequencies, or different modes of vibration, that give rise to the different types of particles. Think of it like this: the strings are like musicians in an orchestra, each playing their part. A violin string, when plucked, can vibrate at different frequencies, producing different notes. Similarly, the strings of the universe vibrate at different frequencies to produce different particles. A string vibrating at one frequency becomes a photon, which is a particle of light. A string vibrating at another frequency becomes an electron, and so on. The beauty of this idea is that it provides a unified picture of the universe. All particles, the constituents of matter, the carriers of forces, everything comes from the same thing, these tiny vibrating strings. So in essence, string theory suggests that the universe is like a grand symphony, with every particle a unique note played by these tiny strings. Now, imagine you're not just living in a 3D world, but in a world with numerous dimensions. String theory is a bold proposition, daring to imagine a universe far more complex than the one we perceive. You see, it insists on the existence of extra dimensions. Yes, you heard that right. Beyond the 3 dimensions of space and the one of time that we're familiar with, string theory postulates at least 6, sometimes even 7 additional dimensions. Imagine living in a house. You're aware of the rooms you can enter, the kitchen, the living room, the bedrooms. But what if there were secret rooms, hidden from view, that you simply cannot perceive? This is the kind of universe string theory paints for us. It suggests that our universe has more rooms, or rather dimensions, than we can perceive. But why can't we see these extra dimensions? Well, string theory proposes that these dimensions are compactified, which is a fancy way of saying they're folded up so small that they're beyond our perception. It's as if the additional rooms in our cosmic house are hidden behind invisible, impenetrable doors. Think of a garden hose from afar. It appears to be a one-dimensional line, right? But as you get closer, you realize it's actually 2-dimensional, with the second dimension wrapped around in a circular form, too small to notice from a distance. That's a glimpse into how these extra dimensions might be hiding in plain sight. The existence of these extra dimensions isn't just for show. They're essential for the mathematical consistency of string theory. The strings of energy that form the heart of the theory vibrate in multiple dimensions. And it's these vibrations that give rise to the fundamental particles we know, like electrons and quarks. So, according to string theory, we are living in a universe with more dimensions than we can perceive, like hidden rooms in our cosmic house. String theory also promises to solve one of the greatest puzzles in physics. Imagine having 2 sets of blueprints for the same house. One set describes every nook and cranny in meticulous detail, leaving nothing to the imagination. This set is like quantum mechanics, explaining the behavior of particles on the smallest scale. The other blueprint, though, takes a broader view. It gives you the house's overall structure, its place in the neighborhood, even how it relates to the surrounding landscape. That's general relativity, describing the universe on a grand scale. But there's a problem. When you try to build the house using both sets of blueprints, things don't line up. The meticulous detail of the quantum blueprint doesn't fit with the broad strokes of the relativity blueprint. They're incompatible. This is the conflict at the heart of physics today. Now imagine a third blueprint. This one takes the best of both worlds. It's detailed where it needs to be, broad where it has to be. It reconciles the differences between the other two, bringing them into harmony. This is the promise of string theory. String theory posits that our universe is made up not of point-like particles, but of tiny vibrating strings. These strings vibrate at different frequencies, And these frequencies determine the properties of the fundamental particles. It's like a symphony, with each string playing its part in the cosmic orchestra. The beauty of this theory is that it can incorporate both the small-scale world of quantum mechanics and the large-scale world of general relativity. It has the potential to unify these two conflicting theories into a single framework, resolving the inconsistencies and providing a comprehensive description of our universe. String theory, then, could be the key to unlocking a unified theory of everything, solving the long-standing puzzle in physics. Yet string theory is not without its challenges and criticisms. As we delve deeper into this fascinating realm of physics, it's crucial to keep a balanced perspective. Let's explore some of the prominent criticisms this theory faces. One of the most significant challenges is the lack of experimental evidence. Despite its mathematical elegance, string theory is yet to make a prediction that can be tested in a laboratory. This is largely due to the fact that the strings as proposed are incredibly tiny, even smaller than an atom, making them nearly impossible to detect with current technology. Another critique is the existence of multiple versions of string theory. Initially, 5 separate versions were proposed, each with its own unique set of rules and assumptions. This multiplicity was somewhat resolved with the introduction of M-theory, which unifies these versions under a single framework. However, the existence of multiple versions continues to be a point of contention among physicists, raising questions about the theory's universality. The mathematical complexity of string theory is another hurdle. It's a mathematically intense field, demanding a deep understanding of highly advanced mathematics. This complexity makes it inaccessible to many and adds to the difficulty in testing and verifying the theory. Perhaps one of the most intriguing criticisms is the theory's inclusion of extra dimensions, up to 11, according to M-theory. While conceptually fascinating, it's a concept that's hard to reconcile with our three-dimensional experience of the world. Some critics argue that these extra dimensions are merely mathematical conveniences rather than actual features of the universe. Lastly, string theory faces the challenge of non-falsifiability. In other words, it's difficult to come up with an experiment that could definitively prove the theory wrong. This has led some to question whether string theory can be considered a scientific theory at all. Despite these challenges, string theory remains a fascinating and potentially revolutionary concept in our understanding of the universe. So, where does string theory go from here? The answer lies in the hands of the brilliant minds around the globe, relentlessly probing the depths of this enigmatic theory. Every day, new discoveries and insights are being made, inching us closer to deciphering the mysterious language of the universe. The current research in string theory is a whirlwind of ideas and equations, all aimed at uncovering the elusive experimental evidence that could propel this theory from abstraction to reality.